Hello, welcome back. Lecture 53 today. So we are going to continue our discussion on Smith chart where we had ended in the last lecture. If you recall, Smith chart is basically trying to convert the rectangular x plus j y of the impedance, the complex impedance, into a polar form, okay, by taking help of the reflection coefficient. Okay, so we learned how to map different points on the Cartesian rectangular coordinate to the polar form. Essentially, you are converting the complex impedance value into a reflection coefficient. Okay, it is a magnitude in a particular angle. So let us come to the whiteboard here. So this is what we had ended the last lecture with, that each and every impedance can be mapped to a certain point on the Smith chart or the polar form. Okay, this is the open, this is the short, and everything else is in between. Okay, so this is how it is. Now a few things that we need to be aware of, and this is open, this is short. Okay, the top half of this Smith chart represents inductive loads. It is basically positive. So we are going to talk about x plus j y sort of a thing on the top. The bottom half represents capacitive load. We are going to talk about x minus j y sort of a form here. Okay, so the top half is inductive, the bottom half is capacitive, okay, purely imaginary. And the way you read a Smith chart is that, suppose I have any impedance, suppose I have maybe 25 plus j 75 ohm divided by 50, that is your 0.5 plus this will be 1.5 j, correct. So what you do is that on the x-axis, on the primary axis, you go 0.5, which is this is 0.4, this is 0.6, so 0.5 will be somewhere here, correct. So that is 0.5, and now it is plus, so you have to go top 1.5. Where is 1.5? You see this 0.2, 0.4, 0.6, 0.8, 1, 1.5. Okay, so this is your 1.5. This line is your 1.5. So what you do is that you take this value 0.5, this is 0.5, and you go like that, this. Okay, so maybe I will change the color here. This point is your this point 25 plus j 75, 0.5 plus 1.5. What if I had say 100 minus j 25, then I have normalized 2 minus j 0.5. So first I will go 2, which is this, and minus 0.5, so minus 0.4, minus 0.6, so minus 0.5 is here, correct. So it will be something like that, and this will be something like that. So this point is your 2 minus j 0.5. So that is how you read. So this, suppose I have this particular impedance, okay, that is my impedance, and everything this one, this is perfectly matched. This is your ZL dash equal to 1, that is your characteristic impedance, that is your match. The idea is that you always want to come to this match condition. Okay, the idea is, suppose I have a point here which is your 25 plus j 75 or 0.5 plus 1.5, alright. So I have a point here which could be, for instance, my output impedance of the device, and I want the device to be internally matched to 50 ohm, because everything is 50 ohm, you want it. So which means from this point I have to come to this point. I want the device has an output impedance of this. I want to add something on the device so that the output impedance is now matched, which is 50 ohm. That is a concept of impedance matching in a way. Okay, I will remove the annotation here, maybe I will explain there are many more things of course, but I will explain just intuitively what it means. Okay, so if I look at 0.5 plus 1.5, that point was this was 0.5, this was 1.5 here. So yeah, this point. So I have this point which is suppose the output impedance of the device, and which is 0.5 plus j 1.5. I want it to internally match it so that the output impedance becomes 50 ohm, so that I can tell a customer or some circuit designer, hey look, I have made an internally matched transistor, that means the output is 50 ohm. Okay. So, I want to come from this point to this point here. How will I come? Okay, there are many ways to come, but you usually try to. So, essentially with the transistor, you have a transistor. With the transistor you are going to implement some network. You have to implement some network of capacitance, inductors, etc. such this is called a matching network. So, that matching network will transform the output impedance of the transistor to 50 ohm. This matching network will transform the output impedance of the transistor, whatever it is, in this case this, to 50 ohm. That is your matching network, output matching network, and there could be input matching network also, by the way. This is called impedance matching. Okay. This is one type. I mean, in some cases you want to match it conjugately to the load. So, your load has certain maybe your load has suppose 100 minus J25, that is your load impedance, and your transistor needs a matching network such that the output impedance will now look like 100 plus J25. The conjugate of this, you know, if one is ZL, the other is ZL star, conjugate. The conjugate of the load, if you match it that way, then you can enable maximum power transfer. So, there are different criteria of course, but here I am generally talking about matching it to 50 ohm. So, how will you match a point to 50 ohm? In general, you try to avoid including resistors in the matching network, because those lead to losses, R square R loss. So, you try to avoid resistive lines. Okay. So, if you go along this line, you are essentially adding a resistor. So, you try to avoid going along that line, because that will mean that you are essentially adding a resistor. So, what you have to do is that you have to take help of a parallel series combination or parallel or series combination of inductor and resistor, such that you can move on either the admittance circle or the impedance circle. So, remember, whatever Smith chart you are looking at right now and whatever we have talked about is in the context of Z or impedance. However, in often cases it is useful to talk about in terms of admittance, in which case the Smith chart can be flipped both as a mirror and as well upside down, and you get something called a Y Smith chart or an admittance Smith chart. I will show you how an admittance Smith chart looks like. But admittance Smith chart does not exist in isolation. At admittance and impedance, both values are plotted together to give you a holistic kind of a Smith chart where you can infer to both admittance as well as impedance values. And when you have such a chart, then it becomes easier to hop from one circle to another circle and come from one point to another point like this here. It will not come directly like that, you have to move along circle. Okay. You have to move along like circle, you have to go this way, that way, and come ultimately to this point. Okay. So, in a way, that impedance matching, we will see how it will become increasingly clear, but you need both admittance and impedance values in order to make it more convenient. Okay. But with that being said, now let us come to another very important concept in Smith chart, which is adding a transmission line. Suppose I have a transmission line, just a transmission line of length L. If I add a transmission line to a say transistor or whatever, a load or whatever, what does the transmission line do? You will see that the transmission line does not change the magnitude of the reflection coefficient. Okay. The transmission line introduces a phase or a shift in the phase, we will see that. Okay. Before that, just for example, I will come to that, I mean this is part of that only. Suppose I have a point here, this point is 0.2 plus 0.6 J. So, this point corresponds to 0.2 plus J 0.6. This is your impedance at this point. If I look at the center, which is this, which is the match condition, if I draw a straight line from center to that, which is this black arrow that you can see, okay, the length of this arrow gives you the magnitude of the reflection coefficient, the magnitude. You remember, I am plotting everything as gamma into e to the power minus j theta or something like that, right. So, this magnitude of the reflection coefficient is the magnitude of this line. But how will you measure the magnitude of this line? The magnitude of this line with respect to the full radius of the circle, which is this. If the entire radius of the circle is this 1, then this is the magnitude, it comes out to be 0.74. If you take a ruler or a scale, you will find out that is 0. And this angle, the angle it forms with this, that angle is this theta. So, that is your 116, in this case this is 116 degree, 0.5 degree. So, 74 116.5 degree, that's your polar form, it's your gamma and theta, that represents this particular value of impedance of 0.2 plus j0.6. Okay, just keep that in mind. Now I will talk about what happens when you add a line. Okay, when you add a line, this is your line, the reflection at the end of the line is gamma 2, the reflection at the start of the line is gamma 1. If you do some simple math here, you know, in terms of reflection coefficient and all, I mean how much is incoming U1, how much is outgoing U1 minus, how much is coming here U2 plus, how much is going here U2 minus, you do some math based on whatever we talked, and you can find out the ratio of gamma 1 by gamma 2, which is the reflection coefficient here divided by the reflection coefficient I am seeing here. That ratio turns out to be this, which is e to the power minus j2bl. You see that the magnitude has not changed. A transmission line does not change the magnitude of the reflection coefficient, it only changes the phase, it only introduces a phase change. In this case it introduces a phase change of theta is equal to 2bl. Okay, that is your total phase change that it has done. And how do you pictorially represent that in the Smith chart? What I mean is that suppose I had a point here, this red point, can you see? By introducing a line of length L, if I multiply 2 by 2bl, that is your total phase, the 2bl gives me this value for instance. Around this center point I will move in this way and I will come to this point. So, this point, this magnitude is exactly the same as this magnitude, because this is the center of the circle and this line has exactly the same length as this line, but the angle has changed. Initially the angle was this, now the angle is this. Okay. So, it has rotated it clockwise. Okay, by adding a certain line of length I am rotating it clockwise here, and you can see that the transmission line has the effect of changing the phase or the angle of the impedance of the reflection coefficient. Okay. So, for instance if I have a length of line as 0.3 lambda, the length of the line is 0.3 lambda, how much phase shift I am going to have? I will have a 2 into beta into L. So, 2 into beta is 2 pi by lambda into length is 0.3 lambda. Lambda gone, this is 4 into 0.3 is 1.2, correct, 1.2 pi. This is the angle, 1.2 pi is more than pi, pi is 180 degree. So, 1.2 pi is roughly more than 180 degree, something like 190 or 200 degree around that point. So, this point around this center point, okay, remember this center point, I am changing I am rotating it clockwise here by 108 whatever 1.2 into 180 degree. So, that is 12 into 18. Okay. So, that is 180 and 206. So, that is 206 degree. So, this angle is 206 degree, or that is also 206 degrees, also 1.2 pi degree, same thing, radian. Okay. So, I am changing it along this line and I am coming to this point, I have reached this point. So, this point is the new point on the Smith chart that I have arrived at because I have added this transmission line of length 0.3 lambda. The magnitude has not changed because this magnitude of this line is exactly this magnitude of this line. So, the magnitude of the reflection coefficient has not changed, but the angle has changed. It has basically shifted my point from here over to the point at here by introducing a delay or an angle shift of 206 degree. Okay. And this point is now 0.4 minus 1.09 j, that is the new. This is a very important thing because by adding a transmission line I can shift a point from one point to another point by keeping the magnitude same. Remember this circle that I am drawing with respect to the center is not the same circles as those circles are different, those are the the constant real part circle with varying imaginary part, that is a different circle. Those circles are not concentric in a way, they are they all meet at this open point. This is a circle that I am drawing with respect to the center here. Okay. So, this introduces this particular phase delay, or you can say shift of the transmission line shifts the phase of the reflection coefficient. Okay. Now, this is the admittance Smith chart, this is the Y Smith chart, this is the traditional Z Smith chart. Sometimes it is much helpful to talk about in terms of admittances because you have things in parallel, connection in parallel. So, you have to invoke, it's desirable to invoke the admittance Smith chart. So, what I mean is that if I have a point Z naught here, any Z here, then this is the center point. If I take a diametrically opposite point here, which means this is some length, I go exactly the same length on the other side of the circle, it is a diametrically opposite point here, then this point gives you the admittance, this point gives you the admittance corresponding to that Z. So, suppose this Z is maybe I don't know, some x plus jy minus jy. This is on the capacitive side. No, the bottom part is capacitive. So x minus jy. If I go diametrically opposite, I get some value here, which is suppose maybe a plus jb. So this a plus jb is actually the admittance of this value. You see my point? 1 by z, essentially 1 by z is the admittance, right. So that gives you that value. So instead of doing this, which might create hassle, what people do is that they flip the impedance Smith chart mirror about the center, and the top becomes negative in the admittance Smith chart, this is negative, and the bottom becomes positive on the Smith chart, on the y Smith chart, which is opposite to the z Smith chart, and you have circles going like this. See, it's exactly. Now if I have a point in the Smith chart, suppose here the original Smith chart, if I combine these two Smith chart again, I just look at this point here maybe, and I can read up this value here and I will get the admittance value, the equivalent admittance value. So what I mean is that, maybe I will remove the annotation, it will become very clear. It is actually very simple here. Okay. So I am plotting the y and the z Smith chart together in this plot. Sorry, okay, I have to go full screen. I am plotting the y and the z Smith chart together here, this chart, okay, this chart. So suppose I have a value here. Now let us focus on the red colored curves, because those are the traditional impedance Smith chart. I go here, this point and then this point. This point corresponds to 1 plus 1. So this point corresponds to 1 plus j1 ohm, I mean normalized, sorry, in the impedance. Now how much is its equivalent in the admittance? I do not have to take a diametrically opposite value, I can just stay there. I can just read the blue curves now, and the blue curves I will have to come from the left side, not right side. I have to come here, okay, this point is here, then I have to go up this. So how much is this point? This point is 0.5, right, this is 0.5, no. So this is 0.5 and I am going up, so it is negative in the admittance chart. I am going up by this quantity, which is minus, sorry, which is minus 0.5, this is minus 0.5, no. So I am coming this way and I am going up this way, the same point. I am not changing the location of my point, I am just staying wherever I was. Maybe I can remove the annotation to make it even more clearer. Okay. So I had this point, I read off the impedance value in the traditional Smith chart, I come here, I go here, I read the value which is this, I stay at that point. I now look at the blue colored admittance curve, I come here, this point, and I go up here. So that is 0.5 and I go up by minus 0.5 because admittance is negative on the top side. So this point basically corresponds to 1 plus j, or its equivalent admittance is 0.5 minus j.5. Very easy. Without changing the location at all, I could read both the admittance and the impedance value at the same point by just looking at two different charts. If the admittance chart is not given to you, then suppose this point is this point, then you have to take this point and you have to draw a diametrically opposite value here. Whatever this length, you have to go the length here, and this point you have to go here 0.5 and again here, which is maybe 0.5. So you come here, this is 0.5 comma 0.5, which is precisely what you got here. So instead of doing this diametrically opposite point and reading the value here, you are directly reading the value in the admittance chart here. So if you have an admittance chart in conjunction with an impedance chart, then it makes life easier because you can read the corresponding impedance and admittance value together, and that is very helpful in designing impedance matching, in understanding the Smith chart. Okay. Now suppose I have this particular structure, I have a transmission line of length 3 lambda, 0.3 lambda. I have a capacitance in series whose capacitance is minus j25 ohm. Remember, this is j omega c. So that is minus 1 by j omega c. So 1 by j omega c is minus j25 ohm at certain frequency, I do not know what frequency. Then I have a parallel inductor and then I have a load here. So the impedance looking at the load is Z1. After I add the capacitor in series, the impedance looking here I am seeing Z2. After I add a transmission line which will only shift phase, not change the magnitude, I see an impedance of Z3, and after adding an inductor in parallel I see an impedance of Z4. How will you navigate this along the Smith chart? This point is very easy to plot in Smith chart. This is J2 minus J 0.5. So from J2 minus J 0.5, can I come to the Z4 and I look here and I see what is the impedance looking into the line? How will you do that? So you have to go step by step. First you plot this in the Smith chart, then you add a series of this, then you add the phase shift of this, then you add a parallel of this. So, when you go to parallel, it is better to convert everything into y, then it becomes easier to add. You convert to y, then you add this j 50 ohm, which is basically j, because 50 ohm divided by 50 ohm is 1 j, and then you again revert to the original z from y and you get the point. Okay, that is what you do. So, you start from here. This is your, this you see my point here, this is your starting point of 2 minus j 0.5. So, this is your 2 and I am coming by 0.5. So, this is the point I am getting. Now, I am adding another minus j 25, minus j 25 is equal to minus 0.5 j. So, I have to add minus 0.5 j. So, how will I do that? I have to go further down. So, from this point I have to go to this point. This is the minus 0.25. In other words, this is this point, this after you add becomes this point Z2. Why? Because this plus this is nothing but 100 minus j 50. Can you see that? So, this is basically 2 minus j 1. So, both of this together is actually 2 minus j 1. So, 2 is this, 1 is minus 1 is this. So, this. So, this point, can you see this? This point is this. Now, maybe I will remove the annotation. Okay. So, this point is this Z2. Now, I will introduce a phase shift of what is the phase shift I will introduce? 0.3 lambda. 0.3 lambda is 206 degree. So, I will keep the same magnitude this, but I will move now 206 degree or 1.2 pi, I will reach here, same magnitude, okay. It is a circle, can you remember that? I get this point Z3, this is my Z3, okay, this is my Z3. Now, what will I do? I have to add j in parallel. So, it is better to convert into y parameter now. So, I am looking at the, till now it was only the red curve, now I look at the blue curve. This Z3 I can go here on the admittance chart, I can read this value, no, this value. So, I will get the corresponding y3. So, I do that. So, I read the value here in the y like this and then like this, I see the y3 value. This is the y3 value, the y3 value comes out to be 1 minus j 1. So, this is your y3 value, great, this is the y3 value. So, after I get the y3 value, I have to add this j there. So, I have to add j, which is this, I add j, I get to this point, okay. I add the y, remember this is along the y I am moving, along the y, I am not along moving the z. So, I am moving along the y, I am adding here j, I am getting it point, this point here in the admittance chart. Now, I have to come back, I have to revert to the admittance impedance. So, I look at the red curve now. So, the red curve is this, I have to go all the way here, then I will go all the way here, can you see that? So, this is point whatever 0.2 plus maybe around this is 0.4 I guess, 0.2 plus 0.4, yeah, right. So, this the value finally I get is around 0.2 plus j 0.4. This is the value looking from here. You have transformed 2 minus j 0.5 to how much? 0.2 plus j 0.4, correct. You have transformed 2 minus j 0.5 to point, how much was that? 0.2 plus j 0.4, you have transformed that by adding this, this and this, okay. Can you see that point? You convert to y, then you add j, then you convert, I mean you look at the admittance chart, in impedance chart now. So, you have effectively done that in a way, okay. Now, there are certain things, rules of thumb when you do impedance matching or when you navigate the Smith chart like that, certain things need to be kept in mind. I am looking at the impedance only, no admittance here. You know the top half is inductive and the bottom half is capacitive, so it is negative. When you add capacitances in series, you are moving along this direction. When you add inductor in series, you are moving along this direction. Why? Because inductor in series tends to move up, capacitor in series tends to move it down, remember that, okay. When you add resistances in series, you are moving along this line, you try to not add resistances. You do not try to move along this line, because when you add resistances you lose I square R heating, I mean the resistive losses come into picture, okay. So, remember a inductor in series will move this, a capacitor in series will move this way, okay. This is what I talked about here. Now, what about parallel? If I have a capacitor in parallel, if I have an inductor in parallel, now I will go to the admittance chart, because that is easier in parallel it is admittance, no. So, in a resistance in parallel will again be this, the resistance in parallel is this, which you try to avoid. An inductor in parallel is this, is okay. and then capacitor in parallel is this, just remember that, inductor this, capacitor this in parallel, okay. In series, inductor this, capacitor this, please remember that. Once you remember that, it becomes quite it becomes quite easier to move along, you know, the direction. So here I am showing you everything, L parallel, C parallel, okay, I will talk about this. So I will talk about series and parallel together. Yeah, this is the series, that was the parallel, okay. So this is the series, that is the parallel, and any transmission line will basically shift the phase of the particular point, okay. It will not change the magnitude of the point, alright. These examples I will do it of course in due course of time, but I had one more plot, maybe I do not have that. So what essentially you need to keep in mind that whenever you have both admittance and impedance chart together, you have to move from one point to another point like that, okay. You have to move from one point to another point like that, for instance. So you have to either add a capacitor or an inductor either in series or in parallel, it is very important, okay. So if I have both admittance, the impedance chart goes like that, correct, and admittance chart goes like that, correct. So you have to move between the two charts when you try to do impedance matching. You have to move from one point to another point, you have to move from another, you know, the admittance to impedance, impedance to admittance, and in this case that is why you have to keep in mind that inductor in parallel goes like that, capacitor in parallel goes like that in the admittance chart, okay, sorry, and in series inductor goes like that and capacitor goes like that, which is this is, okay, capacitor goes like that, inductor goes like that, okay. And your resistors which you try to avoid in general in case of your traditional Smith chart, okay, in traditional Smith chart you will add resistors like that, and in your impedance Smith chart you are going to add resistors like that, okay. So once you are familiar with this movement up and down of adding either resistor or capacitor or inductor in parallel in series, you can go from any point in the Smith chart to any other point on the Smith chart, and that is the genesis of impedance matching in Smith chart, okay. So with that maybe we will end up today's lecture here. We are going to discuss impedance matching with a few solved problems in the next class that you will appreciate how to use Smith chart in doing impedance matching. There are other ways of impedance matching also using numerical techniques, mathematical methods, but Smith chart is a more intuitive method. So we will do that quickly in the next lecture, and then hopefully we will try to move to the passive section, you know, how to there are many things about passives that we have to cover. So that we will do hopefully in the next lecture. So thank you for your time, I will see you.